Everything around us, everything, from the phone in your hand to the air you're breathing, it's all made from a pretty small set of basic ingredients. We call them elements. But how on earth do you keep them all straight? Well, it turns out chemists have a map for that, and today we're going to take a tour. So let's start with a bit of a riddle. What could a solid, shiny car door and the completely invisible air possibly have in common? It sounds like a trick question, right? But believe it or not, there's a deep connection between them. And the answer? It's all right here on the periodic table. See, both the car door and the air are made of elements, but they come from totally different families. This table isn't just some boring old list. It's a map. A map that organizes all the building blocks of our universe into distinct neighborhoods, each with its own personality. All right, first stop on our tour, we're heading to the biggest neighborhood on the block, the one that absolutely dominates the landscape, the metals. Just look at this. It's kind of wild when you see it laid out. Almost everything you see in blue here is a metal. They're by far the largest family of elements, stretching all the way from the far left side and way deep into the middle of the table. So, what really makes a metal a metal? Well, they've got this shared set of family traits. They're shiny, we call that luster. They're sonorous, which is just a fancy way of saying they make a ringing sound when you hit them. They're malleable, so you can hammer them into super thin sheets like aluminum foil. And they're ductile, which means you can stretch them into wires. Plus, and this is a big one, they're fantastic at conducting heat and electricity. Pretty much all of them are solid, with one very famous, very weird exception, mercury, which is a liquid. Now, on the chemical side of things, there's another huge clue to their identity. When metals team up with oxygen, they form something called a basic oxide. Now, I want you to tuck that term away in the back of your mind, basic oxide, because it is the secret key to a much bigger pattern we're going to uncover later on. Okay, to make this all a bit more real, let's look at a couple of classic metals. On the left, you've got sodium. This stuff is so soft and reactive, you actually have to store it in oil to keep it from freaking out. And next to it, magnesium, which is famous for being incredibly light, but also super strong. Two very different personalities, but both are definitely members of the metal family. And they have some really important and very different jobs in our world. Sodium, that's what gives so many street lamps that unmistakable yellow glow. And magnesium's combo of being light and strong makes it perfect for building parts for airplanes and high-performance cars. See? These aren't just abstract ideas on a chart, they're all around us. Okay, time to pack our bags. We're heading all the way across the map to a completely different territory, the home of the non-metals. And as you're about to see, they're pretty much the polar opposite of the metals we just met. And I'm not kidding when I say they're different. Just look at the comparison. Where metals are shiny, non-metals are usually dull. While metals are almost all solid, non-metals can be solids, liquids, or gases. And forget about bending or shaping them. If a non-metal is solid, it's brittle. It'll just shatter. To top it all off, they are terrible conductors. And here's the perfect poster child for the non-metals, sulfur. It's this pale, crumbly yellow solid. Notice not shiny at all, and if you took a hammer to it, it wouldn't flatten out, it would just turn into a pile of dust. That is your classic non-metal. But this is where non-metals get really interesting. Take the element carbon. As a diamond, it's an awful electrical conductor. But as graphite, the stuff in your pencil, it's actually a pretty good conductor. It's the exact same element, behaving in completely different ways, just based on how its atoms are arranged. How cool is that? And this versatility is just mind-blowing. From the graphite that lets you write, to the diamonds used in jewelry and for cutting glass, to the coal that can power a city, all the way to high-tech carbon fibers. Carbon is without a doubt the superstar of the non-metal world. Okay, so we've met the metals on one side of the map and the non-metals way over on the other. But what about those few elements that are kind of living on the border right between these two massive empires? If we look back at our map, you can see them, right here, highlighted in green. See how they form this perfect diagonal staircase? It's like a dividing line separating the huge territory of metals from the non-metals. These are the metalloids. You can think of these as the great compromisers of the periodic table. They're not quite metals, but they're not quite non-metals either. They basically have a foot in both worlds, borrowing some properties from each side of that staircase. And the undisputed king of the metalloids, the most famous of them all, is this guy right here. Silicon. Yeah, at first glance, it might just look like a dull metallic rock, but the unique properties of this one element have literally changed the course of human history. Why? Because silicon is what we call a semiconductor. That means we can control its ability to conduct electricity, turning it on and off like a tiny light switch. And that one simple trick is the fundamental principle behind every single transistor, every computer chip, and every solar panel on Earth. Our entire digital age is quite literally built on this one metalloid. Okay, deep breath. We've met the three main families, but this is where it all comes together. Because it turns out this whole system isn't just a convenient way to sort elements. Oh no, there is a deep, hidden chemical logic that explains why this map is laid out exactly the way it is. Remember way back when we were talking about metals, and I told you to remember the term basic oxides? Well, it's time to pull that little fact back out, because the way an element combines with oxygen, the nature of its oxide, tells its true story. It reveals this incredible pattern that runs across the whole table. To see this pattern in action, all we have to do is look at one single row of the periodic table, period 3. On the far left, we've got a classic metal, sodium. As we move across, we eventually end up at a classic nonmetal, chlorine, on the far right. This table shows us what happens when each of them forms an oxide. And there it is, the big aha moment. As you move from the metals on the left to the nonmetals on the right, the nature of their oxides changes in a perfect, predictable pattern. It goes from strongly basic to weakly basic to this weird thing in the middle called amphoteric, which means it can be an acid or a base, and then it just gets more and more acidic as you get to the nonmetal side. It's a perfect chemical gradient. So, what does this all mean? It means the layout of the periodic table isn't random at all. It's a masterpiece. An element's address, its location on the map, directly tells you about its chemical personality and how it's going to act. That great divide between metals and nonmetals isn't just a line someone drew. It is baked into their very chemistry. Which leaves us with one last little thought experiment. Imagine tomorrow scientists announce they've found a brand new element, and its spot on the map is way down in that bottom left corner. Based on everything we've just seen, what could you predict about it? Would it be shiny or dull? A good conductor? And what about its oxide? Would it be basic or acidic? The map, it gives you all the clues you need to figure it out.